Monitoring, analysis, and tracing. In this topic, we're going to talk about the monitoring methods that we use to extract information on a machine, as well as the optimization tools and the processes we use to optimize a machine, and then to use some of these tools in effect to define and help us perform those tasks as an administrators. So first of all, what methodology might we use when doing monitoring? Well, there's kind of an overall idea of how to do system optimization, and they require that we have a good tool set, a list of things to do, including monitoring, analysis, and tuning of the system. And then we have to apply that not only to the system as a whole, which is all of the processes and applications running on it, but we also have to look at the way that the CPU is being interacted with, the memory, the storage, the network, and so forth. So there's a lot of components here, and it's interesting that we can use a kind of a methodology in order to extract this information. So first of all, what components would be monitoring? Well, we can break them down into different areas. It could be general system optimization. It could be CPU specific functions. It could be memory specifics. It could be I/O specifics. It could be network specifics. And then, of course, we always have to look at the way that applications are running on top of things as well, because, as you know, applications don't always behave exactly as we would prefer. So what are some optimization tools that we would use to work within this methodology or this set? Well, we would need tools that would gather information for us. We would also need something that would help us to digest the information. So tracing, analysis, using baselining tools, doing differentials on files, comparison, and the basic components that would go into that. Those are going to need tools to work. And then we have to have something that can implement the changes that we are recommending in order to resolve issues that may be on a machine. Now, there are two varieties of tools out there. There are those that are supplied by the system, and as a result of it being Linux, there are a lot of tools that can be used on the operating system to extract information like this. We can also create our own scripts or looking in the /proc or /sys directories in order to extract information about either the hardware or software or any application that is running on a machine. So what is the actual act of monitoring? Monitoring is gathering information. It could be hardware specific information. And the reason for that is hopefully very obvious. We want to maximize the hardware itself. We want it to do its best. Now, there are going to be some realistic things here. Obviously, we don't want to spend hours and hours and hours to get a 0.01% increase in performance in most cases. That might be big in some specific areas, but in a lot of cases, that's not big enough to invest lots of time. So there needs to be some realistic ideas there too. Specifically, we might also use monitoring to look at performance, to find what is normal, which is what we defined as a baseline. And then after we put a heavy workload, some machines are very busy first thing Monday morning, say from 9 o'clock in the morning until say 11 o'clock in the morning. When people come in from their weekend, they start working, and this application that's served up by our SUSE Linux box has to be able to respond appropriately. And what is appropriate? You need to know what that is. So that performance baseline has to be done. And we need to know what it looks like when it's under load. And of course, we need to do that over a periodic set of time so that we know that over time it looks like this. And during certain stretches of really hard work, this is what it looks like. Again, part of monitoring a system is knowing what normal is. Now, what is analysis? Analysis consists of several things. It is a way of systematically approaching our environment. And usually this is the method that a lot of people will follow. So we follow a defined process. As an example, a machine is not connecting to the network appropriately. What's the first thing you check? Well, various people would say different things, but a lot of times the first thing that people will say is check the physical. Is the cable plugged in? How many times have you run into a machine that's not behaving properly and network cable simply wasn't plugged in? that's a problem. But that's part of a process that you've defined. Check that physical first. And a systematic approach allows you to make sure or to avoid some of the mistakes that might be made from a more haphazard investigation. And a lot of times we document these so that people won't have to go through the same pain we do when we first discover that something is a problem and we find a method for figuring that out. Now, obviously, there's a couple of things that we also need to do with analysis. We have to know the tools that are associated with analysis. If we do not, what happens is we don't actually allow ourselves to extract the right information. So, being aware of the tools is also very important. We also need to understand the architecture and the subsystems that we're going to be affecting. We also need the effects of subsystem interactions and the potential impact on performance and or stability of a particular machine just by interacting with those subsystems. Sometimes you want to do a profile of the disk I/O, but you don't want to do that in the middle of the day when everyone else is using the system. You might wait until a more optimal time in order to do those kinds of things. So when we're doing analysis, we can use a systematic approach, but we need to know how to use the tools and what tools are available to us and exactly the impact of this analysis is going to have on a given machine. Now, sometimes the thing you don't want to hear is that you're going to have to do a little bit of extra work. And the reason I mention this is good analyzers take good notes, organize them, and they save everything. The reason for this is you don't have to reinvent the wheel or refigure out how to solve something every time. Sometimes you go months or even years without seeing the same problem twice. I don't know about you, but I don't remember everything. Writing things down and keeping them where I can go and refer to them helps. We can also automate performance tool and application tests so that we can reliably repeat them. So in other words, we never skip a step and get an artificial report on how performance is impacted by something. We also almost always want to use tools with the lowest impact or very low impact on a machine. We don't want to artificially increase the load on the machine if we don't have to. We also need to learn to trust the tools. After especially we have some experience with them, we can start extracting which tools produce the best results. We then use the knowledge base of other people's experiences. I've heard of this website. It's called Google. They have this great thing where people who have done things report what their experience was and other people come and learn from it. I know, excuse the sarcasm. It's a good thing when people share their knowledge of how something works or how to fix things. And same thing goes when troubleshooting a machine. Now, reference the internet. This is the last one. It's actually the same point. But I just want to point out that your local people asking your coworker why something doesn't work is okay, but sometimes you do need Papa Google to go and to help you figure out how to resolve an issue. Obviously, validate the source before you proceed because sometimes people give bad advice on the internet. May have heard of that. So we've talked about monitoring, we've talked about analysis, but we can kind of break it down a little bit deeper. There's also investigation process that has to go on. When we are trying to determine what's going on a machine and whether it is doing what we expect it to, we have to start with that baseline. In other words, we have to have previously collected information that is useful to us so that we can compare it to where we currently are so that we can diagnose the problem appropriately. Generally, we start with the largest circle and work our way in. What do I mean? We determine the general problem first, and then we research an ever-shrinking circle until we zero in on what the problem is, and then we resolve the issue. This requires some tuning, where we change the system configuration to affect performance in what we hope is a positive way. It does require us to continue to monitor and analyze the information of what's going on. As we tune something, we should know its impact. This is also what we call an iterative process. We make a change, we check to see its impact. We make another change or further that change and see its impact. That's how we tune for best performance. It requires that ongoing monitoring and analysis. So, what are some basics with tuning? System tuning is an art, and it requires attention to multiple areas, and people with experience generally develop a sense of what it is supposed to be doing. This also goes the same for people who monitor servers. Generally, when people spend time watching a certain subset of machines, they generally have a basic understanding of what it's supposed to be doing and when it's misbehaving. When we are working in this parameter or paradigm of tuning that requires us to carefully monitor and analyze information, we make small changes and we look for problems in that process and we tune that machine as we go. Balance tuning is critical to optimum performance. Now, what is balance tuning? We tune things, in most cases, one thing at a time, but we'll make a change, we'll see its impact. And if there are multiple pieces that affect the thing that we're trying to tune, we'll make a change to, let's say, piece A, see its impact, and then make a change to piece B and see its impact with change A also being implemented. And then we balance that to see if we can get the best performance out of it. Now, it's going to be impossible in a lot of cases to tune for every workload on a single system. You can't tune I/O to be high performance and at the same time also make sure that all network traffic is 100% perfectly tuned as well. Well, you can, but there are going to be some limits on how you can get those two coordinated with each other. You might also have problems where you need high throughput, low latency, or high latency is okay, but even higher throughput on your storage environment. So we have to watch those things. So where do we focus our attention? We disable things that we don't need. If we don't need the GUI, make sure it's not running. Get rid of the extra stuff that's going on a machine and tune based on that and see how that affects your machine. Now, the kernel itself has its own tuning functions to work with. The Linux kernel allows a boot time and a live tuning of its parameters. At boot time, we add things usually to the Linux line in grub, and we set those values. But we can also go into the proc directory and make edits that will change that behavior. We can also insert modules, remove modules, and do other things that will change that. And there are some pre-tuned ideas for general server workloads under SUSE Linux. By default, it is tuned that way. We attempted to set a kind of balance thing, but that doesn't always work. Sometimes you need a very specific tuning, and you can do that with the various tools out there.